Have you ever wondered how a bridge can stretch across a vast river or deep valley without collapsing? How can thousands of tons of steel and concrete remain suspended above empty space? Why doesn't a bridge break under the weight of hundreds of vehicles crossing it every minute? And how do engineers build a bridge before there's even a bridge to stand on? It almost seems impossible. Yet, by understanding and applying the laws of physics, the principles of science, and extraordinary engineering intelligence, humans have transformed the impossible into reality. In this video, we're going to uncover the stages of building a bridge and reveal the physics, science, and engineering intelligence behind every single step, from the first survey of the land to the final load test. You'll discover how every decision is guided by invisible forces, precise mathematics, and brilliant engineering that keeps these incredible structures standing for generations. Stage 1. Understanding the site before building anything. The first stage is not construction, it's investigation. Engineers never begin by pouring concrete. They begin by studying nature. They examine the river, valley, or canyon to understand every force that will act on the bridge throughout its lifetime. They drill deep into the ground to determine whether the soil can support millions of kilograms of weight. If the soil is weak, they keep drilling until they reach stable rock. They measure wind speeds because moving air exerts pressure on every surface. They analyze earthquakes because the earth itself is constantly moving. They calculate future traffic loads, floods, temperature changes, and even the possibility of corrosion. The intelligence here is prediction. Engineers don't build for today's conditions. They build for the worst conditions the bridge may ever experience. Stage 2. Designing the bridge using physics. Once the site is understood, engineers choose the bridge type. This decision is entirely based on physics. A short span may need only a beam bridge. A wide valley may require an arch bridge that converts weight into compression. A very long crossing may require a suspension bridge, where cables carry the load through tension. The design is chosen because of how forces move. The bridge becomes a machine that controls invisible forces. Engineers calculate exactly where every force will travel before construction begins. Stage 3. Designing the foundation. The strongest bridge can still collapse if its foundation fails. That is why the foundation is the most important part of the structure. Engineers drive enormous steel or reinforced concrete piles deep into the ground until they reach solid rock or dense soil. These piles transfer every kilogram of the bridge's weight into the earth. The bridge is only as strong as the ground beneath it. The physics is simple but powerful. The load must always be transferred to a material capable of supporting it without excessive movement. Stage 4. Building the piers and towers. Once the foundation is complete, workers construct the piers or towers. These structures act as the bridge's vertical skeleton. Their purpose is not merely to hold the bridge up. They redirect enormous forces downward into the foundation. Every vehicle crossing the bridge increases the downward load. That load travels through the deck, into the piers, then into the earth. The towers are carefully shaped so that the forces remain balanced instead of concentrating in one location. Stage 5. Constructing the main structure. Now engineers begin building the bridge itself. Steel girders, arches, trusses, or massive suspension cables are assembled. Every component has one specific job. Some members resist compression, some resist tension, some prevent twisting, some stop sideways movement. The genius lies in assigning every material to the force it handles best. Concrete excels at compression. Steel excels at tension. Together, they form a structure far stronger than either material alone. Stage 6. Connecting the bridge deck. The bridge deck is the surface vehicles travel on. Although it appears to simply support traffic, it performs a much greater task. It collects every load from cars, buses, trucks, and pedestrians. Instead of allowing those loads to remain concentrated in one place, it spreads them over a much larger area. This reduces stress on individual components. The deck acts like a distributor, sharing weight throughout the entire bridge. Stage 7. Controlling gravity. Gravity is the greatest force acting on a bridge. Every second, gravity pulls everything downward. Engineers cannot eliminate gravity. Instead, they guide it. When a truck enters the bridge, its weight immediately begins traveling through the structure. The force moves into beams, into cables, into towers, into foundations. Finally, it reaches the earth. The bridge is essentially a carefully designed pathway for gravity. Stage 8. Controlling wind. Wind behaves like a moving fluid. As air flows around a bridge, it creates pressure and swirling vortices. These forces can make the bridge vibrate. If engineers ignore aerodynamics, Strong winds could produce dangerous oscillations. That is why bridge decks are carefully shaped after extensive wind tunnel testing. The objective is not to stop the wind. It is to allow the wind to pass around the bridge smoothly. The bridge is designed according to the science of fluid dynamics. Stage 9. Preparing for temperature changes. Steel and concrete expand when heated. They contract when cooled. A bridge hundreds of meters long may change length by several centimeters between a hot afternoon and a cold night. If both ends were fixed rigidly, enormous internal stresses would develop. Engineers solve this by installing expansion joints and bearings. These components allow controlled movement while keeping the bridge stable. The bridge is designed to move safely rather than remain perfectly rigid. Stage 10. Protecting against earthquakes. Earthquakes send waves through the ground. If a bridge were completely rigid, those forces could cause catastrophic failure. Instead, engineers use flexible bearings, seismic isolators, and dampers. These devices absorb and dissipate earthquake energy. Rather than resisting every movement, the bridge moves with the earth in a controlled way. The intelligence lies in managing energy instead of trying to eliminate it. Even after construction, the bridge is not immediately opened. Engineers inspect every weld, bolt, cable, and concrete section. Heavy test vehicles are driven onto the bridge while sensors measure movement, vibration, and stress. Laser instruments detect tiny deflections. The bridge must behave exactly as predicted during design. Only after every result matches the calculations is the bridge approved for public use. Stage 12. Continuous monitoring. A bridge is never truly finished. Throughout its lifetime, engineers monitor cracks, corrosion, cable tension, vibration, and structural movement. Modern bridges contain sensors that continuously collect data. If unusual movement or stress is detected, engineers are alerted long before a serious problem develops. The bridge becomes an intelligent structure that is constantly being observed and maintained. The genius behind it all. Building a bridge is not about stacking concrete and steel. It is about understanding gravity, force, motion, materials, wind, temperature, water, and the earth itself. Every stage depends on physics. Every decision is based on mathematics. Every component has a specific scientific purpose. A bridge stands not because humans are stronger than nature, but because engineers understand nature's laws so well that they can use those laws to transform what once seemed impossible into something that millions of people trust every single day. The world is full of incredible engineering, science, and hidden intelligence waiting to be uncovered. If you enjoyed this video, like, subscribe, and turn on the notification bell so you never miss another fascinating explanation. Keep asking questions, keep learning, and I'll see you in the next video.